Okay, we get to Node TCP. Let's dive beyond TCP here and discuss how TCP works in the first lecture, in the first part of the lecture. And then we dive into examples of how Node perceive TCP and how does it work with TCP. It's always a very interesting when you have a fundamental understanding and you start using the applications and you understand that it's just everything is just packets at the end of the day. And this understanding then solidifies the fact that there is a cost to everything. And it just feels good as an engineer to understand. Let's jump into it. All right. So TCP is this beautiful protocol that pretty much 99% of everything that has to do with networking is built on top of. Now, so any protocol that you ever can think of that you're sending data on top of is using TCP. That is HTTP as being the primary one, TLS, HTTPS, well, DNS uses UDP, but DOH uses TCP, right? And what other? SSH. The examples go and know those. Like this is the primary, protocol for transmission. It's just a stream of bytes that goes from one file descriptor to another side of the network. And using these four parameters, source IP, source port, destination IP, destination port, you uniquely identify packets coming in to that particular application. See, the TCP was designed to address not only machines, because that's what the internet protocol is for. It addresses a whole machine, and the concept of machine really changed, right? What does a machine mean? But think of it as a box. But then you want to address specific applications within this machine, and ports came into the picture, and TCP took advantage of this concept of the port. So it's a stream base, it's a layer 4, it's right above the network layer. So this is where the TCP layers it at layer 4. This is where ports are being exposed. This is where the transmission happened. And we have the ability to address processes in a host, right? If you have an IP, you can address a host. If you have a port, you can address processes within the host, which is pretty cool, right? If you can think about it. And TCP has this control aspect of this, right? And control means it controls this transmission, not just allows you to send anything, but it controls the flow. Because if it's a stream of bytes, then we need to control it. How much bytes can I send? Can the destination handle it? Can the network handle it? So there is a flow control and there is congestion control. Two types of control, right? UDP doesn't have that. It's a message protocol, and hey, I'm sending you something, and I don't care if you're overwhelmed or if you can't handle it or the network can't handle it. It's someone else's problem to deal with that, right? And here's the thing, it's a connection based. So you need, because we segment the stream into chunks, right? The stream cannot be just sent as like a fire hose of bytes, right? We segment them into what we call segments, TCP segments. And then these segments has sequences on them. 1, 2, 3. It's not literally 1, 2, 3. It has to be like a little bit larger numbers. And these numbers is critical because what is not mentioned here is TCP deals with ordering. So if 3 arrived before 1, 3 to 1, the client side or the server side can actually order the segments based on how the client actually sent them. So 1, 2, and 3 must arrive in that order. Okay, and that's essentially the most important part. And because we need to start with a sequence number that to label the segments, we need to exchange those sequences between the client and the server. And this exchange happens in the TCP handshake, and that's when we agree on an actual connection to establish a connection. So we can exchange this parameter, so we can exchange the synchronization number, so we can exchange the window sizes and all of that stuff. If you want to learn more about TCP, check out my network course. I go into more details, and I don't want to do that here because I won't focus on Node, right? I'll just give you an overview of TCP here though. Yeah, so yeah, most protocols are built on TCP or UDP. So here's some use cases. If you want reliable communications, TCP is your friend. Remote shell, SSH, right? If I'm doing SSH, I'm using TCP. I want things to be reliable. If I'm connected to the database and Postgres, I'm going to use TCP, right? And I want things to be reliable. I want things, when I send something, I want it to reach. I don't want to deal with late arrival in my application. I want the kernel, or let's say the TCP stack, to take care of reliable communication, and TCP does that. And the implementation of TCP is baked into the operating system kernel. The kernel does that, which is very critical to understand, that there is this implementation of TCP IP, and it's done in the kernel. This has been moved to the kernel a very, very long time ago, right? For performance reasons. So yeah, databases, web communication, pretty much any bidirectional communication happens on TCP. And I say bidirectional because it's a stream of bytes, right? You can send bytes, right? And then B can send back stuff as long as you have a connection. And as we said, the connection has like certain parameters that you have to satisfy in order to do that. And there's a handshake that happens before that connection can be established. So let's talk about the TCP connection. We must create a connection before we send any data. And that is very interesting to understand because there is a cost to that. You'll see me always repeat the importance of understanding cost, right? To understanding how much it costs to do something. Always understand that. So a connection is identified by 4 properties. There is always a source IP. There is always a source port. This defines the client side socket. And there is always a destination IP, and there is always a destination port. This defines the server side or the backend. You need those 4 in order to establish a connection. And in your building applications, you might notice that you almost never deal with these 2. You always do specify a destination IP. Sometimes you don't even do that. You just specify a host name, and DNS takes care of that to translate that for you as an IP. And sometimes you don't even specify a port, because by specifying HTTP : / right? HTTP. This looks like kanji. This is not English, right? If you do this scheme, as they say, by giving me this, I implicitly know the default port of HTTP, and that is 80, right? And by default, if you said S, then I know it's 443, right? So you don't even need to specify these, but we know. In deep internal, we know what the IP is, and we have to give them. So it all goes back to what I said in the previous lecture, which is the mapping. You map something to something. You need this mapping, because at the end of the day, we have to have numbered ports and physical IP addresses to connect to, and then we have to have source IP and source and port. And this the kernel often takes care of that for us if we don't specify it. But you can, if you want, you can, and I think I'll show that in not this TCP, I'll show it in the UDP lecture, how to actually bind to a source port of your choosing. And this is represented by a socket. And we're gonna have a socket in the client side and a socket in the server side. We kind of talked about that, right? And in order to do the connection, we need to do the 3-way handshake. So let's talk about that. So we're going to talk about the three-way handshake in a minute. But before we do that, the TCP composition, what is inside it? We have this beautiful things that's called segments, TCP segments. And these are sequenced and ordered, right? And if they happen to be unordered while we transfer them, the receiving side will take care of the ordering of these segments. So there is cost to ordering, of course, right? And here's another thing I didn't mention. Segments are acknowledged. So if you send me segment number 5, I acknowledge the server or the client can acknowledge, whoever the receiver is, can acknowledge segment number 5. And that tells the sender that, hey, I acknowledge that I received 5 and lower. That's the definition of an acknowledgement. You have received this segment and anything below it. So if I sent 1, 2, 3, right? If I sent segment 1 and I sent segment 2, 3, and the receiver only got, let's say, only got 3 and 1, what does the receiver send back as an acknowledgement? You cannot send 3 because that indicates that you also got 2 and 1. You didn't get 2, so you cannot say acknowledge 3. But you do acknowledge 1 because you got anything before 1. Might be a bad example, but let's say there is a segment called 0, 0, right? So let's say we received 0 and 1, but not 2 we didn't get, but 3. So if you, in this case, you acknowledge 1, and that means you acknowledge both 1 and 0 and anything below it, right? And lost segments are retransmitted if something is lost. And the definition of lost is also very interesting. What does that mean? Right? You can get into a large discussion, and then people might disagree and agree on that because it's a timeout, right? You can wait. If you waited long enough, then you might get it. But if you don't, then if you waited a long time, you might just delay your transmission, right? So at some point, it's like, hey, if I don't receive this within 300 milliseconds, I consider the segment lost. And as a result, the client will resend it, right? And here's a critical thing. Segments are not messages. You cannot treat it as a unit of work. Because if you send a request, like an HTTP request, it may be broken into 7 segments. Or if it depends on the segment size, which is really how to define a segment size, the MSS, as they call it, the maximum segment size. It really depends on the network health. Sometimes the network will support 1500 MSS, a little bit less than that. Sometimes the network doesn't handle it and supports only 500. You don't know that. Sometimes you're in a beefy data center and supports 9,000 bytes segments. They call jumbo frames, to be specific. But yeah, so you cannot control the segments, right? So one message will be broken up into segments based on whatever the network condition. So don't treat one segment as a message, right? So that's very critical to understand. And the reason I say that, because I made that mistake and I don't want more people to get into that problem. But nowhere they talk about this stuff, so I have to spell it out to make it clear. Let's talk about the connection establishment example, right? So here I have a server, a client 10.0.0.1, and I have a server 10.0.0.2. When it comes to application, when we look at this from an application point of view, you can see that the same server can host an SSH server on 222, an HTTPS server on 443, and an HTTP server on 80. 3 processes, right? And we can listen on this particular 10.0.0.2. So we have 10.0.0.2, 20, 443, and 80. So 3 sockets, 3 listening, binding socket ready to be connected to, right? And then we'll come to this part later. Okay? And then in the client side, one client could choose to connect to a destination. And in this particular case, in my app 1 wanted to connect to app X, which is SSH, on this server. So what we do is we generate a local port which is 5555 in this particular case. And then, and then 1000, and then we have 10001 as the source port, and the destination becomes 10002, and the destination port is 22. So we're connecting these guys together, right? How do we do that? Well, you need to do a connection establishment, and you need to send, this is how it looks like as an abstracted way. This is the IP packet, and inside it there is, this is the IP packet, right? And inside it there is the TCP segment, which has the destination port 22, and we have the destination IP 10002, and I want to go to 22. So this particular app I want to go to, okay? And we identified it by the destination port, and the source port is 5555, and the destination source IP is 10001. Okay, and then you send something called SYN, which stands for synchronize. This is called the SYN segment, and this is a start that says, hey, I am interested to actually establish a connection with this port. Now, if the port is open, the kernel will respond back. We have no business here as applications. As Node, if Node is running here, right? If Node is running here, it doesn't do anything. It just listens. That's the only thing Node does. The kernel responds to the SYN and SYN application request for us, right? And it does that by responding back. It says, yes, this port is open. Someone is listening on it. I will reply back. And you said the destination IP in this particular case is, you flip them, because now we're sending a segment back, and that segment will go called SYN-ACK. SYN-ACK means I am acknowledging your SYN, and now I'm sending my own SYN. And there is like a bunch of synchronization numbers, because you cannot always start from 1. That's not secure. Not that TCP is secure to begin with, but you don't want people to guess the numbers. It's back when they thought things were secure, but it's not, right? So they start from a large number, so that is not, things are not predictable, right? So as they start, you can start with 1 million, right? And the client can start from 3 million, whatever, a big number. And then they exchange these numbers, which is not shown here in that, but this say, hey, this is my source IP, this is my source port. It's just flipped, right? The source IP becomes the whatever was the destination, and then the client finally sends a final ACK to the same thing, port 22, destination 10002. There you go. You have a full-fledged connection, which this creates a file descriptor in the client, but only when it has been accepted, right? Well, this particular case. When Node calls function called accept, which is through epoll, it will of course poll the socket and says, hey, is this socket ready? Yes. The kernel will say, yeah, there is a full-fledged connection ready for you to be accepted. And that's when you get a file descriptor, whatever, 20 assigned, right? That's when you get a file descriptor. And here, immediately, there is no accept here. You just you get the connection, because you initiated it, right? You created the socket locally, and you set everything. The server side is different. So that's the three-way handshake. And you can see there are different local ports connected to different applications. Right? It's all similar. There is a command to list all the connections as well. Sending data. So how do we send data? So let's say I am connected to this SSH port, and I'm sending ls, which is command to list something, right? So what we do is we encapsulate this data into the TCP segment, which is inside this, right? And the green thing is the segment, right? And then we wrap it in an IP packet, right? So if you think about it, it doesn't look like this. It's more like this. This is the data. But I like to show it this way because it's more visually appealing. It's like a Matryoshka, whatever it's called, Matryoshka's dolls, right? And things inside each other. But yeah, you send the command, and then what happens is the application here, it's not really Node, but it's SSH, but you know what I'm talking about, right? It calls read on the socket, and it takes whatever it takes. I had to realize that it's going, the pointer is going nuts. So yeah, it takes whatever is there and it sends us to the application. And then when we do that, the kernel actually sends back that, hey, I actually got your ACK, and it will use the sequence number of whatever the current sequence number, because it will keep increasing, right? And then we ACK it, and then the data will just be copied to the user space and be consumed. Now, the app here has flow control that says, well, am I ready to send more data? And it all depends on this ACK thing, right? Because as you send data, the client thinks, oh, I don't know, I didn't receive an ACK. Maybe the server is not ready to send something. So you get delayed, right? And that's how things essentially work with flow control. It gets really complex, and it's a whole algorithm with flow control. There's more examples with acknowledgements. So in this particular case, I sent 3 segments with 3 sequence numbers: sequence 1, sequence 2, sequence 3, right? Sequence 2, sequence 3, these guys. And let's say we got all of them. We got 1, 2, and 3. But in this particular case, we don't send acknowledge 1, acknowledge 2, acknowledge 3. That's a waste. So because we got them at the same time, we only send 1 ACK. So yeah, acknowledge 3, which indicates to the client that we got all of them. And there is an RFC that literally delays the acknowledgement as much as possible, so that it doesn't send a lot of acknowledgements, right? Which caused other problems when that was implemented, delayed acknowledgements, right? Because things start to slow down. Because you wanna slow down the acknowledgement sometime to get as many segments, and you acknowledge once, but that will create delays. So you might want to acknowledge whatever you have, but then the more data you receive, you end up acknowledging, and then there is a lot of traffic. There's no longer a problem these days because we have good networks, but back in the days, it was a big problem because we don't want a lot of traffic. I'm too late for that. We have a lot of traffic on the internet. Here's some example of a lost data. Let's say sequence 1 was sent, sequence 2 was sent, but sequence 3 was sent, but it was never received. Let's say one router in the middle got that, but failed to read the bytes, or a fluke happened and we lost it. Maybe it's corrupted, right? So it never forwarded it. So we got sequence 1, sequence 2. In that particular case, we only acknowledge 2, right? Which acknowledge 2 and 1. But then this tells the client that, what about 3? I sent you 3. Well, I don't know. I just got 2. That's what it means. So the client will send 3 again. And that's where basically it was called retransmission. So interesting stuff. And all of this stuff, don't worry about it. It's all taken care of by the kernel. Here's how you close a connection. It's a four-way handshake. You do a fin, and then the server replies back by an ACK. And then you do another fin. The server does its own fin, and then replies with an ACK. And these can be combined into one. These two sometimes can be combined with a one. Sweet. Here's the pros of TCP. I just like to add them. There's guaranteed delivery. There is flow control and congestion control, which I didn't discuss in this lecture. It's just too much for content, right? Take my network course if you're interested. But yeah, there's a congestion control. There is a window size. There is a receiver size. It's like, how much can we actually send? And it's all changing up, fluctuates. And there is a slow start algorithm. And there is the congestion avoidance algorithm. It's a whole thing, with TCP. It's just it's easy to understand once you get an idea of it, but there is so much there. It depends on your interest. Like, do you really need to know? Sometimes it's like, hey, if it works, unless it's causing me a problem, then maybe I need to dive into it and understand it. Right? And order packets, no corruption, and our app level work. I don't need to do anything in my app. It just takes care of this stuff. Compared to UDP, which we're gonna do in the next lecture, it has a larger header size. The TCP header size is larger than UDP because of all this window sizes and length fields and the sequences and the options and all that stuff. So it is a larger header field, up to I think 40 bytes or something. And yeah, it's sometimes considered high latency because of these algorithms, right, for certain workloads. And it does too much at a low level. This flow control and this ordering specifically is a little bit too much for a single connection. And the reason is because you don't have control at the application. Sometimes you need this low level control brought up into the application, like the ordering. Like sometimes when you send data, right? Let's say you're sending a request, right? You're sending actually HTTP requests. So this is one request, this is another request, and it's composed of multiple segments, right? And there's a third request, right? You're sending them all together. I want these to be ordered. I want these to be ordered. I want these to be ordered. But it doesn't matter if this guy arrived before this or this as a unit of work. It doesn't matter. Because yeah, they are independent stateless requests. So it's request 1, 2, 3. Let's say I'm labeling the request. So if 3 arrived before 2, sure, go ahead and execute it. But that's not how TCP works. 3, if you send 1, 2, 3, and these have a collection of segments, what you're gonna get is if 3 arrive first, the kernel will say, wait a minute, what happened to 2 and 1? What happened to the rest of the stuff? It will block, it will wait, and it will not acknowledge anything. It will just say, hey, I didn't receive anything, right? So what will happen is the client will be waiting until we receive all the segments, and then we'll deliver all of these 3 to the application in order. Oh, right. And then the application will say, oh, we have 3 requests. We unnecessarily blocked 3 from being transmitted to the application, which is Node in this case, just because we needed them in order, which is not the case. So we needed to separate this. We need this guy to have its own stream, if you will, and this is its own stream, and this is its own stream. We need these streams to be its own units. And that's what Quick did. TCP, if you think about it, it's just a single stream, single connection, right? So if you have a connection, TCP, you have just single stream, right? So you cannot do multiple streams in the same connection. That doesn't work. So what Quick does is literally that, but they built it on top of UDP. That's all what they did, right? I say that's all. It's not simple, right? There's a lot of work that went into that. But yeah, they wanted an idea to create multiple streams, and they want to send a lot of streams, data in that stream, and that should be ordered. But if I'm sending stuff in the other stream, that shouldn't be, or they have nothing to do with stream 1. They can be arriving in different order, and essentially that allows, HTTP 3 to be born. Right? HTTP 2 was built on top of TCP and has this problem, which is called the TCP head of line blocking. Too much information. Let me know when to stop. All right, let's talk about Node TCP. So Node TCP is exposed via this net module, right? And HTTP and DNS and other protocol uses this net module, as we actually used it ourselves, right, in this course. And then what we have is you'll always eventually end up using sockets and TCP and UDP. Like even if you don't feel it, but we end up always using it. So the server creates a listening socket, the client creates a connection socket, and then we connect to each other. All right. So we're going to go through a TCP client example and understand that you can build, if you want, your own HTTP client using the TCP net module. Because it's just connecting, creating connection, sending stuff, and then receiving stuff. So here, what we're going to do is we're going to reference the net, and then we're going to create a connection, specify the host, and this is the host, example.com, which does a DNS. in this particular stuff, right? When I'm of course we need an IP. This means nothing to us. This string means nothing. We need an IP. So DNS kicks in behind the scenes and does a DNS to get us an IP, right? And then we send the port, and we give it the port 80 in this case. And just doing that will be done in the poll phase. Remember, because it's an IO, especially there's DNS involved. When we do that, that's when we send the SYN and SYNAC and all that stuff. We'll do a create connection, and that will do that work. And then when we get the full-fledged acknowledgement, and we got the acknowledgement, that means, hey, we have a connection. Then we create a callback. Well, the callback is already created, but it's set as not ready. That the receiving of acknowledgement, the final acknowledgement of the three-way handshake, tells we mark this callback as ready. It says, all right, poll phase, whenever you're back here after your loop, come pick this up and boo, connect. Okay, and then execute it. And that's where we get this message. And you get also the connection object, of course, filled. This will be filled with stuff, which you can use, which is pretty cool. Here's a server example, and I want you to pay attention to that. We create an empty object, create server, and then we bind it. And binding is essentially the idea of listening on a specific IP and a specific port. Right? This particular thing, I'm explicitly binding the socket to 127.0.0.1. That means I only want people to connect to me on port 8080 only on 127.0.0.1. So if they use a different IP address that I may have, they won't be able to connect. And sometimes you want to do this because, say, you have like an admin API that you don't want anyone to connect to except those who are in the same machine. Like if you're SSHing into the same machine, then you can consume this API for security reasons, right? There is no business for people to expose that. One common bug or problem that people run into, they spin up a Mongo cluster on a cloud and they listen on ports, which including the public IP address port, which then opens this to exposure so anyone can connect from anywhere in the world, right? So for that particular thing, you want like databases. You really want to listen only on specific IP addresses that are local to a specific network so that you can remote in and only connect from there. Does that make sense? So yeah, we bind it here. So like in this part example, you can connect on 120.0.1, but you cannot use the IPv6 loopback to connect. Yeah? And then of course we get, this is an event that when a three-way handshake happens and the kernel gives us a connection and node calls accept, and the connection file researcher is created, then we mark this callback as ready, which will pick it up in whatever the next event is and the next loop is, and we start executing it. Okay, and then here you get the actual remote port, which happens to be the client, right? Remote in this case, because we are a server, the remote is the client. And there is another callback where we can set up for when we receive data, right? So when I call read on the connection, the node calls read on the connection, that it will just move the data from the kernel to the user space, which is node, and then it will feed it to your callback. And then when someone calls the callback, you get that beautiful data that we just asked for. How about we do some exercises, you guys? So TCP, we talked about TCP in general. We talked about node TCP, how it's behave with the net. And let's do an example of a client and server. And I want to do, for this particular one, you guys, I want to do two things. I want to do TCP dump because I want to see what is being sent from my machine, right? So let's pay attention to that. In order to do that, we're going to use the TCP dump, right? On another window, I'm going to do TCP dump, and I'm going to listen on my interfaces. I already wrote the command here, right? -I says, hey, I want to listen to this specific interface, which is the Ethernet. And this is my Ethernet. And if you want to find your Ethernet, you do show IP address, right? Oh, so show IP. Pretty sure it's called show IP. Oh no, it's IP address show. And this is my IP, which is my local IP address that I'm connected to. That's what I'm interested in, right? And this is my Ethernet. So you can just do that, right? So you can do sudo TCP dump -I, and you do this interface. That's the first part. Then you say, hey, I'm only interested on host that has this IP address, 168.7.79, which is the same IP address as this guy. And I am listening on port 80 because the first example, we're going to connect to port 80, right? And -n means show us numbers, don't show us strings. So let's go ahead and do that. And you have to do sudo because it's an elevated permission to do this operation. And then now I'm going to vim 18 was the TCP. Yeah. What do we have? We're creating a connection to example.com to port 80 from this machine. So we will capture the handshake in this particular, okay? And then after the connection happens, we're just gonna print connect three-way shake full-fledged, and then we're gonna write an actual HTTP valid request get /HTTP11 host www example. I'm implementing an HTTP client in this case. This is how it looks like to actually send an HTTP request. And then when the data appears, I just print it. So let's go ahead and run this. Node 18 TCP 180 TCP, and sure, let's do an strace too. Strace -t -n -f sure. Let's do that. We got everything, and this is all the DNS work that we already talked about. Then after we do the DNS, we're doing a sock stream, which is TCP, right? Streaming at TCP. We're connected to this IP address. That's the IP address we happened to pick in this. So it better matches when I look at the TCP down. It better matches that. And then I'm just writing. I should see the right here. I'm writing something. This is the screen. Yeah, there you go. We're sending. We're writing something. There you go. This is the socket. Socket 37. Socket. We're writing socket 18. That's the connection. And then we're adding. We're listening to some more, and then we got the response. All right. And all of this is happening on the same thread. The main thread is 144. So now what happened in TCP dump? We did you read it like this. It's line by line. And it's just not big enough for me to actually show all of this. So that's what we get. So we sent, this is how you read it. It captures IP packets, right? And the IP packet has 127.179, and this is the local port 46462, just a random number between 0 and 65,000. And then the destination happened to be the same IP address that happened the DNS picked, 96.7.128.175. Is this what we picked? I think that's what it is, right? That matches. Like, this is what we picked. Out of all of these puppies, we got a lot of them when we did a DNS. All right, we got this, we got this, we got this. And then we picked this one at the final one for some reason. I wonder if there's like a pattern, like we always pick the last one. That'll be funny. And then we said the S, the flag is S means send. And then do look at these massive sequence numbers that we send. The window size, the option. And also we send the maximum segment size. 1460 is my segment size, which is like pretty much yours is going to be the same. So the server responds back, because 80, and this is the IP address of the server, respond back to me, because that now this is flipped, right? With a send dot. Send dot means acknowledgement here, okay? send ACK, and this is its sequence number, and this is it's also there is an acknowledgement number sequence number, right? So this is a different one. And the window size is like, hey, send me up to 65k, 65 kilobyte. I support that. This is my MSS. And then finally, the client responds with 0, and then you see P means push. We're sending data. So the client did send something, and very naturally, and TCP dump told us what it does sent, and then the server replied with an ACK, and then it sent, after a while, it sent us back the response. And you can see that it took us 100 millisecond, whatever this is. That's a massive thing. Is this milliseconds or what? 7, yeah, it looks like, yeah, 2 milliseconds. This is microseconds. Right? Took 2 milliseconds to respond. It's fast. And then, of course, we just did that. And then if I close the connection, let's actually, because we're waiting here, right? Because we're doing a poll. Why? Do you guys remember? Because there's a connection open at the client side. You didn't do anything with it. So either kill it like this, forcibly, which then sends the notification that, hey, I want to do a FIN-ACK, ACK. I want to close the connection. And this is how you close the connection. This is a clean close. Sometimes you see an R, which means reset. That's something bad happened. All right. Isn't this cool, you guys? I love this stuff. What else? What is the other example? TCP server. Let's do a TCP server. Here we're listening on 127.0.0.1. I don't want to do that. You know what? Let's do that. Let's listen on 127.0.0.1, port 8080. So we need to change these games to say 8080 instead of 80, right? And hopefully we can capture that. I don't think we will. So we might need to change this IP address to, you know, let's remove the host altogether. Oh, we have to remove the and here. Okay. Sweet. And I am going to node 181 TCP server. This TCP server is only listening on the loopback version 4 because 127.0.0.1. That means, man, I have to also create another tab. Then SSH again. Sorry, hold on, guys. Good. So now I'm gonna do a telnet because it's a server. Let's do first 192.168.7.79.8080. That fails. Why? I'm connected to the same server, right? But it's not listening on that IP address, although that's the same IP address, right? But if I do 127.0.0.0.1 works, right? I can send stuff. And you probably got something here. Yeah, got some data. And we got a new connection, and I printed the source port, sorry. If I close this, closing telnet is always weird. All right. So now if I connect to, let's say, I think it's like this. That fails because their IPv6 is also not supported. We're not clean listening on that. So what we're gonna do here is I'm gonna modify this guy, and I'm gonna listen specifically on my IP 192.168.7.179, or was it 197? I can't remember. All right, now, oh, we forgot to show the TCP dump. We didn't capture anything for some reason. I guess loopback is different. Oh no, that's why, because we're listening on the wrong interface, you guys. Right? So let's see. If you can change this to be the right interface, and you're gonna listen to it. That's why we didn't get anything in the loopback. That makes sense. Now I'm gonna connect to 127, which fails. I'm gonna connect using this, which also failed. But now I'm gonna connect using this, and it works because now I am using the correct IP address. You might say, Hussein, I don't care. I just want everything to work. Let's see if this is capture. Still didn't capture it, huh? Because that while we're listening on the right host, I think that interface it's not, because the packet is not going outside, is TCP dump is not capturing them. That's my guess, I think, at least, because we are listening on 8080, right? Yeah, it's just not capturing. But I bet, like, if I come from outside from my machine, let's try that. This is my machine. I do telnet 197.192.168.7.79 8080. Well, that failed for some reason. Did we stop the connection? Yeah, because we stopped it. That's why. All right, let's run it again. Then I do this. It works. And then we capture it. So even though we're listening on that particular IP, if the connection coming from within the server, it doesn't, TCP dump doesn't capture it unless you're listening on the loopback. Okay, so watch out for that. So yeah, these are like pretty interesting example. And you might say, Hussein, I don't care. I want everyone to connect. And if you want everyone to connect, all you have to do is just literally remove that other part and just say, hey, 8080, which we talked about that. What that does is like, of course, the message is wrong now. If I connect, this works. If I close, oops. If I try 127.0.0.1, that works too, right? And then if I try, I think that's how you do it. Yeah, I keep forgetting how do you do loop back. I think it's like that. Yeah, that's the IPv6 loopback, right? And if I ever know the IP address of the IPv6 version of the whatever, if I have that, which I'm not sure if I do, like what is IP address show? Do I have an IPv6 here? Looks like this is the link local one. I don't think we have an IPv6. Well, there is an IPv6. What do you know? There is an IPv6. So if I do that and I say, hey, telnet, again, this is all test. I never tried this before. Yeah, I have to like specify it in a way such that, hey, this is my. That's actually the gist of it, right, guys? If you have an IPv6, which I really think this should be it. This is the link local one. That should be it, but I don't know why it didn't work. Although I'm listening to all IPs. Anyway, you guys, so that's basically the lecture for TCP. I hope you enjoyed it. And TCP is very interesting protocol. And then if you have time, just like play with these exercises and change them. You'll find okay, yeah. If you have time to play with these things, I mean, yeah, guys, if you have time to play with this, you will appreciate TCP. But just it's very hard to do when you're in a deadline and you have to submit a project. But if you're like having fun with this course, just take some time, an hour, just play with these exercises, change the values, look at stress, look at TCP dump, look at the values, and ask questions and be curious. You cannot be curious, I suppose. It's a curiosity is either there or not. But yeah, I love this stuff, and I hope you do too. And yeah, see you in the next one. Goodbye.